Okay. Okay, this is what we were discussing last time. We just saw the definition of DFT, discrete Fourier transforms, and we were discussing some properties of DFT, if I remember correctly, right? So today we'll see DFT in some more detail, and then after this class, we will be in a position to apply these concepts to real world signals, like mostly audio signals. Let me make a new note. How do we make a new note? Okay. Today we are going to study DFT and SDFT. Oops. Okay. So let's write down the DFT again. So what is DFT? Any signal x of n which is non-zero between a range 0 to n minus 1, right? So it is non-zero in the range n minus 1 and 0 otherwise. So we can represent it as right? So this is our discrete Fourier transform. And we can find the inverse Fourier transform also. That if given xk, can I find xn? The answer is yes. You sum over all the k. Oh, plus we have to add one normalizing constant. That's it. These are the Fourier transform pairs. This is called DFT, and this is called the inverse DFT, IDFT or inverse DFT. Right? So both of them are known to you. Now let's look at some of the examples of DFT. In the last class, we did not do examples, right? Okay, let's see some examples. Let's say my x of n is delta at some n naught, right? So which means, let's say 0, 1, 2, so on up to some n naught. At n naught it is 1, everywhere else it is 0. This is my x of n. How will the DFT look like? So the DFT will be, so I will say, so what is my xk? Find out and tell me. I know it's very easy, just do it quickly. Yes? Just put in the formula there. Yes? Done? What's the answer? This is simply the integration over a delta function, right? Or summation over the Dirac Kronecker delta function. Simply put n equal to n naught, that term will be non-zero, every other term will be 0, simply. So this is basically equal to e to the power minus j 2 pi k upon capital N. And here instead of n, you will have only n naught term. When n is equal to n naught, only that term will appear. All other terms will be 0, right? So that is my Fourier transform. Now, let's say if n naught is equal to 0, which means my impulse happens exactly at 0, what will be the Fourier transform then? 1. It is 1. So if you can correlate it with the what is it called? The Heisenberg's uncertainty principle in physics. You might have studied that whenever you know the position exactly, momentum is not known. When you know momentum exactly, position is not known. Actually, the mathematical foundations of that principle is here in the Fourier transforms. Right? So whenever you know x exactly, it's a discrete function, it's just known exactly, then xk is 1, which means it is spread everywhere. Now see the other example. Let's say my x is a sinusoid. Some f naught or n naught. How do we call it? Some n naught. If my x of n is this, what will be my x of k? So my x of n is simply cosine signal. Means, of course, something of that sort. What will be my Fourier transform? First. Done? N?
What is N naught?
N naught is a number.
Length of signal?
No, N naught is periodicity or the time period of x of n, time period of this cosine signal. Right, because when small n is equal to n naught, then it becomes cos 2 pi. One cycle is completed. Done? No? I would say master these concepts now because they will really help you a lot. Develop the mathematical rigor as well as intuition, both. Done? Okay, I would like to tell one principle which you can use later also. Whenever you work with cos, multiplication becomes very difficult because cos into cos, you have to use some trigonometric identities. But the easier way is convert it into exponential using Euler formulas, and then your life becomes very easy because multiplication is just addition in the exponential space. Should I do it? So I can write cos as e to the power j theta plus e to the minus j theta upon 2. E to the power j 2 pi n upon n naught plus e to the power minus j 2 pi n upon n naught divided by 2. Let's take the first term and find out the xk for the first term. Let's call it x1k is equal to e to the power j 2 pi n by n naught e to the power minus j 2 pi n k upon capital N summation over all n equal to 0 to n. This capital N is different from n naught. Now that's what you want to find out, right? So this is equal to 2 pi right? Is this correct? And summation so you know the exponential of this term, when you sum over the entire thing, it will be 0 if n upon n naught minus k is not 0 or not a multiple of n, then it will be equal to 0, and it will be non-zero only when they match, right? So this will be equal to n if right, and otherwise it is 0. Is this correct?
Inspired, and we considering the second part, I mean, to the power minus j2 pi.
This part?
Yes.
Oh, we just I'm just trying to find the, because Fourier transform is linear, right? You can take Fourier transform individual terms and then add them up later. So this is x1k. Similarly, I can find x2k, and the total xk will be x1k plus x2k, right? Okay, so this is my xk. So this can be written as n times delta k minus n by n naught, right? Likewise, you can find x2 of k, which will be, if you repeat the whole thing, just see that one sign becomes negative. So k will become minus n upon n naught, then only it will be true. So n times delta k plus, so our total xk will be equal to x1k plus x2k. Linearity by 2, yes, thank you. Okay, can you plot this? Let's plot it.
So how is that 0 in any other case?
What is 0 in any other case? Because, okay, let's say my k is not equal to n upon n naught. It is some number r, a non-zero number r. No, it's not equal to 0, not equal to capital N, r. Then summation of e to the power j2 pi n r upon capital N sum over n equal to 0 to n minus 1 will be equal to 0.
So that comes
When
when r is an integer.
r is an integer. Yeah. Yeah. Yes. Yeah, okay. Yeah, you're true. You're right. It may not be exactly 0, but it will be a very small number. Right? That's why you will see, yeah, you're right, that it may not be exactly 0. Because, okay, how I see it is in this way. You know the roots of unity. So these are the roots of unity. E to the power, let's say, e to the power j 2 pi by n times r, where this r is some non-zero number. Maybe now in this case, depending on n upon n naught, it could be a fraction also. And let's say k is 0 or something. Then I'm just taking all the vectors on this circle and adding them up. Their sum will be definitely less than capital N. Why? Let's call this as omega, right? Okay, let's say n is 1 here. Let's call this number as omega. So it becomes 1 plus omega square plus so on plus omega to the power n minus 1. This is, and my claim is that this magnitude is less than n. Do you agree with this? This is simply what is called Cauchy-Schwarz inequality, right? Sum of complex numbers is less than, mod of sum is less than or equal to, sum of mods, right? So simply using that, I can see that. Okay.
So, what if R is, say, 2L?
If R is 2 times capital N, R is 2 times, yeah. If R is either 0 or capital N, then it will be capital N. This term will be capital N. So let's say when you say R is 2n, this means my n naught is what? Let's say k is something, n upon n naught. N upon n naught will be always less than capital N, right? Always less than capital N. So that minus k cannot be capital N, larger than capital N. Okay. Good question. So think in this way, and then you can understand how we plot it. Now, can you plot this? Yes, you have to plot xk. Plot xk. Done? Xk will be difficult. Plot mod of xk. Means xk is a complex number. Just draw the mod. With this assumption that this is n and 0. Of course, we know that it is not exactly 0, but a small number. But okay, assume this is 0. Done? What has discrete values? Xk has discrete values in this case. Yeah. Yes.
So how is it a complex?
Okay, because when we say 0, I said this is not exactly 0. It's maybe some complex number. So okay, if you assume that equal to 0, then yeah. For this thing, yeah, xk is same as xk mod. Imaginary part is 0 in this case. Yes. Done? Tell me, how does it look like? Pardon?
0 dot minus n by n naught and n.
Yes, 0 at all points except minus n upon n naught. Now, see, this when we talk about DFT, it has a limited range, 0 to n minus 1. There are no negative k values here. So, can you refine your answer?
N minus n upon n.
Yeah.
It's only non-zero at n by n.
It is non-zero at n upon n naught. Okay, let's say somewhere here we have n1 n naught. Here you have, this is the height is capital N. Everywhere else it is almost 0. Height is n by 2. Oh, I'm sorry. N upon 2. Thank you. Yes. What else? Any other point? N minus n. Okay. So now this DFT is always periodic. So if something you're saying minus n, so sorry, minus k, if somewhere minus k it is non-zero, then capital N minus k will also be non-zero. 2 capital N minus small k will also be non-zero. But of course we don't consider anything outside 0 to n minus 1, so we don't care about those values. We only care about whatever is within 0 to n minus 1. That's why, so my n minus this term, which is n minus n upon n naught, it also becomes important. All right. So I get 2 peaks, everywhere else it is 0. And if you now do the real plotting using computer program where you do not assume those values to be 0, you may get something like this. Means it will be non-zero around this peak. Like the peak will have some kind of width, and then, but it depends. Sometimes you may get what is called the side lobes also. Something like this. But yeah, the peak will be anyways here.
So n by naught is not an integer, then you have any peaks, right?
You will not get exactly the peak, but you will get maybe regions around the peak. Right? Let's say this is my peak. I may not get this sample, but I may get these samples. Right? I may not get this sample. Right? Okay. Yeah, that was the thing. Now, let's see some properties of DFT. Let's see some properties of DFT. First property is linearity. That's what we said, right? Let's say we have A times x1n plus B times x2n. Then their DFT will be, what will it be? It will be A times, yeah, x1k. Let's assume that x1k is the Fourier transform of x1n. So x1k plus V times x2k, right? And another property is circular time shift. Let's say I move my xn by n naught. I move it in a circular fashion. So whatever I do in the DFT space, it is circular. Means when I move x somewhere here, then this part which is kind of, let's say this is my window. If some x moves here, whatever is the part which has gone out, it will come back in from here. And this comes from the theory of DFT. So when we derive DFT from general Fourier transforms like DTFT, then these properties naturally come. Right? So basically, the principle is that my x of n is periodic with the periodicity capital N, and my capital X of k is also periodic with the periodicity capital N. Right? This is kind of implicit periodicity depending on the what value of capital N I choose to take the DFT, that is kind of, I'm imposing this periodicity on my signal. Right. Okay, so tell me now, what is the effect of circular time shift? If I take the DFT of this, what will happen to my x of k? Yeah, so what happens is it becomes x of k e to the power minus j I. This phase term gets added. This phase or angle gets multiplied. Right? So time shift leads to phase shift. Means, what do you say? Time shift here leads to the angle shift in the Fourier domain. Right? You can prove it. The proof is not difficult. Should we do the proof? Or can you do it? Simply start from the basic formula of DFT. Then you know the formula for xk in terms of x of n. Now you have to find the new like x dash k or x1k, which is the Fourier transform of this xn minus n naught. And you can very gracefully find out that it is actually equal to that by just assume n minus n naught equal to m and things like that. Okay, then another property is duality. So you have seen that the formula of deriving xk from xn and deriving xn from xk, they look so similar, just a negative sign has changed. So let's say if somebody gives me a Python code for DFT or FFT or DFT, can you modify the code or just use the same code for deriving inverse FFT also, inverse DFT also? I gave you a black box code to find DFT. Can you use this code to find inverse DFT? That's the question, right? If I give you the xk and I give you a black box program to compute DFT, can you give me x of n? That's the question. So this is what duality is. So yeah, yes, something of that sort. So let's say if my x of n goes to x of k when I take the DFT, when my x of k goes through the same function DFT, what do I get? I get n times x of n. Right. Actually, I don't need to write this modulo thing because it is implicit, but still I am writing it explicitly so that you don't make any mistakes. Which means if you want to find x of n, so you reverse the x of k and divide it by capital N, and then you will get x of n back. Right? You can derive it very easily, right? Okay, next is time reversal. I will just state them and you can kind of derive them on your own. Time reversal means if I x of minus n, implicitly it is modulo capital N. If I take the DFT of this, what will be my DFT? It will be x of minus k. Again, the modulo thing is anyways there. X star n, the DFT will be x star of minus k. Okay. Now using these, tell me if x is real, what can you say about x of k? If xn is my real signal, means it is not complex conjugate or not a complex number, it's a real number, means it is imaginary part is 0 basically. Then what can you say about x of k?
xk conjugate equals x of minus k.
Oh, you remember from the past course.
Can be derived from.
Yeah, it can be derived, but how could you tell me so quickly? You remembered it or?
I mean, I remember it also, but I also.
Yeah, means. Yeah, okay. Because yes, so basically your xn star is equal to xn, so x star minus k is equal to xk. Oh, good. Yes, it is obvious, yeah. You can see from here. Okay. So basically your x star of minus k, right? So what can you say about the mod xk? The absolute value of xk. This is equal to absolute value of x of minus k, because absolute value of x star is same as absolute value of x. So this is equal to absolute value of x minus k. Now this is very important. This property is very important, that my xk is equal to x of minus k in magnitude space. The magnitude spectrum is symmetric, right? That's a very important property. And since we know this is periodic, so this becomes equivalent to x of n minus k. Because you know you have this n thing here. So means xk is equal to xn minus k. Now just verify it with your cos 2 pi n upon n naught. So in this was a real signal, right? Does it satisfy that property in the xk? Do you have it symmetric? So x of n upon n naught is equal to x of n minus n upon n naught. That property is satisfied in the magnitude space, right? So that's very interesting property. This means, okay, so now let's see from the engineering perspective. If you want to store spectra of some real signal, audio signals, if my real signal has got length capital N, how much memory space, or let's say if to store the real signal I need n memory spaces, how much space will I need in the Fourier space if I want to store the spectrum, n by 2, but because this n by 2 has two components, real part and magnitude imaginary part, so it's twice of n upon 2, so it's n only. Right. So you will need n spaces only to store the Fourier transform, but you are only storing half the spectrum. You don't store the complete spectrum. Just half the spectrum is sufficient because other half is just a mirror image. Okay, we'll see some of these properties in our real audio spectrums. Now we will discuss another property. So whenever we have audio, whenever we have audio, we want to do some kind of processing to the audio, right? It could be amplification, it could be noise reduction or filtering, right? So which means I have to pass it through some linear system, linear or non-linear, but okay, linear, let's say, for the sake of analytical studies, it can be linear system. So when I pass it through the linear system, what happens to my output? My output is a convolution of my input with the system's impulse response, right? So let's discuss convolution also. So in DFT space, in DFT, we will not have convolution, we will have circular convolution, right? So how is it defined? I'm calling it a YC because it's circular convolution is equal to summation m equal to 0 to n minus 1 x of m and h of right. Same as the linear convolution, but just that you have now modulo operations there, right? Whereas my y linear n would have been this is the linear convolution, right? This was the original thing which we learned. But in the DFT thing, it becomes a circular convolution. What is the relationship between the two? Okay, now I can write this as m equal to 0 to n minus 1. If my x of m, I know it's only non-zero between 0 to n minus 1. Right, so this is my linear convolution. So everything is same, only the modulo thing is extra. So what is the relationship between YC and YL? What is the relationship between YC and YL? Okay. I will just derive something and then you will see the relationship. So let's see my YC of n. It is this thing. I can write it like m equal to 0 to n minus 1 x of m. Because m is anyways lying between 0 to n minus 1, so there is no point of writing the modulo thing. But h of n minus m, when I change the value of n, it will kind of move outside the window. So something else will enter, or this part will enter from the other part of the window. So this will become, can I write it like this? Summation h n minus m minus some integer multiple of capital N writing this as this. Can I write it like this? Right? So let's say my original h of n was something like this. When I take modulo, then I will make the, so this window is moving, right? It's like getting reversed and moving. So, but if I want to take modulo, then means within this window, this will move, but whenever this goes out, something else will enter. So let me add that thing which enters also. Likewise, when this window, when the H moves there, then something else will enter. So like now you move your window anywhere, you will see H of n will kind of be a circular thing, right? That's what we are doing. So original H of n was only single thing. This was only H of n, But if you take all three of them, it becomes h n minus m minus r n sum over all r. You basically create copies and then this way you have put. Okay? So let's now take the r out. This becomes equal to r equal to minus infinity to plus infinity and summation of m. For a given value of r, the thing inside is kind of fixed, right? Oh, okay. You can see it like this. I will do some readjustment now. Where is my pen? So instead of writing this, I can write it as n minus rn minus m. Right? So what is this? This is equal to summation right? My circular convolution is basically you take the linear convolution and take its copies after every n window, right? Let's say my linear convolution was something like this. Then let's say this is 0, this is some n. Then this will become, this was my yl n, and my yc of n will become copies of this 0, n, 2n. So first thing, this one comes, then this one comes, then b. This one comes. It becomes the copies.
So the overlapping part gets added.
Yes, yes. So that's the point. So you see here, things are modified. Right? How do we avoid this? It's called aliasing, just a technical term. How do we avoid this tail kind of entering from the other side and disturbing the signal?
Sampling at a frequency must be greater than the sampling frequency must be greater than twice of maximum frequency.
Okay, that is the sampling thing. What about the windows capital N? In terms of capital N, I should choose my capital N large enough so that these copies don't, like if I take my n here, right, then what will happen? The copies will be like this. No overlap, right? Things are very safe. So what is this? The condition is my capital N should be greater than or equal to the length of yn. What is the length of yn? Length of y linear convolution n. What is the length of yln? X plus h minus 1, huh? Okay, good. So this is equal to length of x plus length of h minus 1. So my capital N should be greater than or equal to length of x plus length of h minus 1. So in real life, when you are doing your convolution using DFT on your computer, you make sure to take your capital N larger than this number. Right? Otherwise, you will get aliasing, which means your final output will be distorted. These are some important principles which will greatly affect you later. Okay, then how do we perform convolution? We can either compute these equations, this xm hn minus m summation over all m, or we can do via DFT. So what is the circular convolution? So the circular convolution is represented in this way. YC, and this is also written as x of n, right? X of n, like make a circle. When inside the circle you write capital N, whatever capital N you want to choose, and then write h of n. Right? That is how we write circular convolution. Now what is the DFT of circular convolution? This is also n point DFT, the same n. What is the DFT? Do you remember it from previous results? Yeah, with product. You can derive it also. It's a very simple derivation. You can derive also. xk times hk. That's it. So basically, if you want to filter a signal, which means you want to pass it through some system which has an impulse response h of n, you just take their DFTs with a large enough capital N, multiply them, multiply x of k with h of k, and then take the inverse DFT, and you get y of n, right? But the only requirement is that my capital N should be larger than length of x plus length of h minus 1. Okay. Now I recorded audio of 1 hour at a sampling rate of 44,000 kilohertz. How many samples you get? What is the length of x? 44,000 into 3600. Approximately 10 to the power how much? 44,000 is 4 into 10 to the power 4 plus 3, 4 to the power 7. So 10 to the power 8 approximately. So my capital N should be greater than 10 to the power 8. My computer will die if I do such kind of processing, right? Is there some way out by which we can, let's say my h of n is still a short signal, but x of n is very long. H is short only, maybe of length 100, 200, that's it. But x is 10 to the power 8. So what should I use? I use something called overlap add method. So what is overlap add method? You say my x of n is you split your x of n into small windows. I represent every window by xw, like within the window. You can choose the window length, whatever you want. But this window length will be the length of x of n. So if you roughly know what your capital N should be, let's say I want to keep my capital N equal to 1024. My h of n is only 100 or 200 something, right? So which means I can choose my length of x to be 800 or something, right? Let's keep this as of length 800, right? W. Then I can say my y linear. Okay, so I'll just I will just write it explicitly. If this condition is satisfied, then what happens? Then yc of n is equal to y linear of n. Ultimately, I want y linear of n only, right? I want y linear of n only. I don't want the overlapping effects. So, but the yc why it appears because I am using DFTs to compute my Fourier transforms, etc. to basically carry out this convolution. I use circular convolution or DFT based convolution. Therefore yc appears. I don't want yc, I want yl only. But because my tools give me yc, so I just I apply this condition so that my yc is same as yl. Ultimately I want yl only. So yln is equal to x cross h, sorry, x convolved with h. Now it is summation over W, XW, N, H, M. So I can write this as equal to I take my YL and I add them. I add all those windows. So let me draw it pictorially. Let's say my X was something. My H was something small. I need not draw it. Okay. Now I take my small windows of length W. Right? And for each window, I compute my Y. It could be a little longer than the window because it's window length plus length of H minus 1. And then this was my, from the first window. My second window gave me something else. My third window gave me something else. Just add them up all together. It's the final answer. Now in this case, this is not aliasing. This is the length of n. This is n. This is length n. This is length n. Your W is less than n, right? This is not aliasing. This is the natural answer which should come. Right? From that formula you can see that you will have some overlaps which you should get. Those overlaps are not unnatural. Then that is not aliasing. This is called the overlap add method. If you want to see more details about it, some examples about it, go to the lecture videos which I have shown in the beginning of the class. Those videos contain some examples also. But I've just pictorially drawn something just to give you an idea. So generally what you would do is, if I want linear convolution, I will take XWK and HK, multiply the two, take the inverse DFT. Right, this will be my Y of n and sum over all W's, windows. That is how I will be doing it algorithmically. Okay, I hope you remember, why do we use DFT to find convolution? We can simply compute the convolution directly, right? Why do we use DFT to find the convolution? It is faster. Computational complexity of DFT is n log n, whereas the computational complexity of convolution will be n square. So you get so much of reduction in computations. Why not? So why not use DFT to do that? Okay. Yeah, that's it. And finally, I will be discussing short time Fourier transforms. Yes, we are there now. What is short time Fourier transform? Okay. When we take Fourier transform, what it will tell you, what sinusoid frequencies are present there, right? If you have a cosine, okay, good question. So let's say if I give you x of length 10 to the power 8, and you have to now convolve it with h of n, which is of length 200, let's say. So if you do, if you do it using circular convolution, you compute the DFT of this, multiply them, take the inverse DFT. What is the window size you will need? Yeah, at least length of x plus length of h minus 1, 10 to the power 8 plus 200 minus 1. So of the order of 10 to the power 8. It's a huge window. It means your computer will require so much of memory to even store these values, the vectors. Right. In this case, you can process them and throw them away. You take a small window of X, take a small window of H, find their Fourier transforms, small windows. When you compute them, find your this y of w, and throw away all these values.
DFT is faster than convolution.
Why DFT is, oh, that is a different question. We'll answer that later.
DFT we need if our if x is of length n, capital N naught, then DFT will be larger than N naught. It has to be larger than N naught.
DFT, no?
Let's take this let's take the convolution of xn and h of n. If x is of length N naught, then the final DFT will be definitely larger than N naught.
Oh, basically you're saying that we will take capital N equal to N naught plus length of H minus 1. So it is.
Will be that many,
Yes.
k index will be from 0 to that large number, right?
Yes.
So here we will not throw it away, we have to store each index here also.
Here, yes. So finally we are storing that length, the length of 10 to the power 8 plus something. But in intermediate processing is all saved, no? What was the complexity of your FFT, DFT? N log n, 10 to the power 8, log 10 to the power 8. So many and what is the memory requirement of your algorithm? Algorithm also has intermediate terms to save, no? So that will also multiply, add up. So but here, those things are avoided. Another advantage is that you can use it for real-time processing. Real-time, let's say I'm speaking and you are processing it simultaneously. But there you have to wait. After 1 hour only you will process. Okay. Now, short time Fourier transform is, generally, I think you have seen the video. I have shared the video on STFT in before one of the classes. So I will just briefly tell what is STFT. So generally you have signals whose characteristics are changing over time. When I speak, I don't speak just sinusoid. I'm speaking so many things, right? So it's changing. So you want to capture all my things and study them properly. So therefore STFT is very useful. It will take a small window, do the spectral analysis, take next window, like that. So take a small window, find the spectrum. Let's say it's a cos. So you will get 2 peaks, right? Or let me take half the spectrum only, so I will get only 1 peak because other half I'm not drawing. So I got 1 peak. And then I took the next window. It could be an overlapping window also. I got another, maybe the frequency changed. Here the frequency was 100. After some time my frequency changed to 120. After, in the next window, my frequency changed to 110. So now what I will do is I will just kind of take the transpose them. I get a peak at 100. I get a peak at 120. This is 0, let's say. I get a peak at 110. And I will put them together in like an image. Right? So this one comes here, this one comes here, this one comes here. So I get a peak at 100, peak at 120, peak at 110. So this is called a short time Fourier transform. I represent it by x, k, comma, m. So what is x, k, comma, m? Summation n equal to 0 to n minus 1. Okay, so this is basically, you have your x n. Your wn is a window of length, capital N. So wn. It could be a square window, right? right? Where amplitude is 1 always, or it could be a Gaussian window. It could be so many other kinds of windows possible. I think we have seen some of these windows in that lecture, so I will not repeat it. That's it. That's it. STFT done. Okay, now we will see practical. Oh, what is the time now? 7, right? We have 7 or 8 more minutes to go. Okay, I want to discuss now the Prat thing. Are you able to use Prat? Okay, some assignments, 2 assignments for you. First assignment is write down real-time pitch estimation. I will sing and you have to tell me what pitch I am singing. Let's say I am saying maybe your screen should show me it is 100 hertz. Then I increase my frequency and it should show me now it is 120 hertz. Then it should be 130, 140, whatever. So as I am changing my frequency, my speaking frequency, in real time it should show me what is the pitch. Let's start with the Prat. Let me new object, record mono sound. Okay, save to list and close, and view and edit. You can see it on the screen, right? So you see, it is plotting pitch offline. I recorded it, later it is plotting, but I want to do this in real time. You should plot the pitch or display the pitch value in real time. Can you do that? Maybe not plotting, but at least, okay, show me the value on the terminal on your screen, that now the value is 100, then now the value is 500, or 150, 170. It should be shown on this, just print it on the screen. Can you do that? This is assignment number 1. Assignment, so how will you do real-time audio capture? To capture audio in real time, you can use a tool called PyAudio if you're using Python. It's a wrapper around port audio, which was originally written for C++ or C. Right? There is a library called port audio in C or C++, and PyAudio is a Python wrapper. So which means you don't have to write the C++ code, you can directly write a C code and you can process it. This PyAudio thing is available online, means the library is available, and there are also example scripts available where you can directly just copy paste that script. It's very easy to understand. Just understand it and implement and kind of run it. You will be able to capture the audio stream in real time, and you can also generate audio stream in real time. Means your Python program is generating the values and it is getting out through the speakers. Right? So PyAudio will allow you to do that. Now, this was assignment number 1. Second assignment is make an infinite loop beat generator. Let's say I'm clapping. This is single sound, right? Now I tell you that, okay, clap after every 1 second. And run this in an infinite loop, right? And what is the periodicity? I will specify whether it is 1 second or 1.5 seconds or half a second or whatever it is. I can specify, and you have to just maybe make a knob, just like you have a volume control knob in your audio system. Like this is a this frequency control knob, where you're controlling how frequently you should clap.
The knob should be in real time.
Knob should be in real time, yes. It's a real time knob. Just turn the knob and your clapping speed will increase. Turn the knob, it will decrease. Without breaking the flow. Not like you stop the program and then again it starts. That breaks your rhythm. Rhythm should not break. Okay? So these two.
Capture the sound also?
Huh?
You have to capture the first clap and then.
No, this is just generator using the knob. Knob means you simulate the knob maybe with a slider or something.
Basically, we have a periodic function to just change the frequency of it. Or no? Like we have a basic clapping rhythm and you just make it faster or slower.
Yes, yes. And that clapping signal can be given to you separately. Means I can just tell you, okay, take this clapping system or this clapping audio basically. I can just give you one file of some short length. Using this file, plus I will specify what is the, how many claps per minute, right? These two numbers, these two things should be sufficient for you to generate that infinite loop of clapping. Okay, these two assignments are there. Now, you go back, explore, and come with your questions. Questions like mathematically, how do we estimate pitch from a short window? How do we, what is pitch, etc., etc. And then in beat generation, how do we do real-time synthesis, or I don't know. There can be so many questions you may have. Ask those questions. Okay. Theory is given to you, but the practical thing will kind of make you think deeper. Okay, this is one thing. Now, another exercise you should do is, there is still time, right? Okay, we will take 5 minutes extra, no problem. I have plotted this STFT on the screen. Can you see it? Let me take a short window here. You can see the function is periodic, and my pitch values are here, and the STFT looks like this on the background. Now, if I go to spectrogram here, I can go to advanced spectrogram settings. It has an option, window shape. What kind of window I want to use? Can you see it? Do you want to use a rectangular window, Hamming window, Bartlett window, Welsh window, Hanning window, Gaussian window? These are all signals, means a kind of windows. And you can use any one of them. Let me, before go to window type, I will show you what is the effect of window length. Spectrogram settings. Window length here is, what is the window length? It's too small, no? I don't know how to make it larger. It is 0.005 seconds, which means 5 milliseconds. What is the window length? 5 milliseconds. If I change the window length, what will happen? If I make the window length larger, what will happen? What will happen to my STFT? Yes? It will be? Did you not watch that original video which I sent you? The videos which I sent you on the second class, in the first week, Thursday class, when I was sick. I sent you some videos to watch. It seems nobody watched those videos.
The boundary between frequencies and
Yes. So if I take larger window, time resolution will reduce, but my frequency resolution will increase. You can see that here. Let me take a window of length 0.05, 50 milliseconds. What do you expect? The peak will become sharper here. See, the peaks have become very sharp. Right? I know my frequency is 128 hertz, right? So let me zoom in that frequency range. Again, I go to spectrogram settings. My view range is 0 hertz to, let's say, 500 hertz. Okay. I can see very clear peak here. Let me make it 1000 hertz just to zoom out a little bit. Right? You can see multiple peaks. Why multiple peaks? Because my original audio is not an exact sinusoid. It is sum of sinusoids. That's why I'm getting harmonic peaks here. So in this way, now I can take a larger window, let's say 100 milliseconds window. What will happen? Very sharp peaks. You see the width has reduced. Peaks have become very sharp. But of course the time resolution will become poorer. Okay. Now let's change the window type. Let's change the window type. In advanced spectrogram settings, you have here Gaussian window. If I use square window, what will happen? What do you expect? Side lobes will appear. Huh? You can see so many side lobes have appeared. Right? Earlier those regions were whitish, now they have become extra lines. So many fine lines have appeared. They are side lobes. Okay. Yeah, so play around with these things, and I am showing it on Pratt. Can you do it on Python? On Python there's a library called Librosa. Use Librosa library to plot the spectrograms, to understand the spectrograms better. Stop, don't move. Wait, we have one more thing to discuss. Yes, and that thing is, there was a video which I shared with you. This one. How many of you saw these? How many of you went through this kind of tutorial? If you have not gone through it, just go through it. It's a very useful thing to study, to understand how STFT or DFT behaves. Now see, this is something I want to share with you. Harmonics. You have a triangular waveform. Because it is not perfect sinusoid, you will get multiples, right? But you are getting multiples at 1 hertz, 3 hertz, 5, 7, 9, 11. But what about 2, 4, 6? Where are they? They don't appear here. Now look at square waveform again, 1, 3, 5, 7, 9. But if you see a sawtooth waveform, all the harmonics are appearing. 1, 2, 3, 4, 5, 6, 7, 8, all are appearing. Now this is the time to challenge you. Tell me mathematically, why is this behavior? When will you see some harmonics are missing, and when will you see all harmonics are present? Use DFT to derive the condition. So theory is there in front, the practice is there in front of you. Theory you know, you have read. Now you have to bring together theory and practice and tell me, why do you have some harmonics missing in some cases? Or when do you have harmonics missing? All right, we stop here. Any questions? So just a reminder, a recap. So you have 2 assignments now, means there are 2 assignment problems. You have one theory problem here, and you have one exercise to use Pratt as well as Librosa to play around and see how spectrum behaves when we change these parameters of DFT. You don't have to submit the Pratt or Librosa thing, that's for your practice. Your performance will reflect when we have some later evaluation. The assignment thing, for that, maybe take 1 week. It's not very difficult. Simple pi audio and then you are done. We take 1 or 2 weeks. Thank you.
Good.